Before the
It's like awesome. Incredibly fulfilling. Just a radio
Okay, it's great to see everyone, and we just had a fantastic talk by Michelle Vick, and she will speak in a few minutes. We learned a lot from her already, and we'll learn some more. We'll start with Haowen Zhang from Arizona that will tell us about a new empirical dark matter halo galaxy supermassive black hole connection from all the way from redshift 0 to 10, although it might continue even beyond that. We have to see from the Webb telescope and Chandra perhaps. And then we hear from Dian Triani from the CFA, who will talk about dust contribution to the FUV-FIR mission of the dusty sage galaxies. And then we'll hear from Rowan, who is visiting us from Ohio State University. Where is it? Oh, right there. And he will tell us about the valued-added catalog of ASAS-SN eclipsing binaries. And finally, we'll hear again from Michelle, and she's from Northwestern, and she will tell us about modeling the irradiation instability of protoplanetary disks. Haowen, please go ahead.
All right. So can everyone hear me okay? Mm-hmm. Okay, thanks. So yeah, thanks for the introduction. And I'm Haowen Zhang from Arizona. So primarily, I'm working with Peter Baruzzi. And today, I want to basically talk about the Trinity model, which we have built in the past few years, trying to connect dark matter halos, galaxies, and supermassive black holes from today's universe to redshift 10. So basically, what Trinity tells us is how big the supermassive black holes are, and at the same time, how fast these supermassive black holes are growing in different galaxies across cosmic time. So firstly, why we should care about how big the black holes are in different galaxies. Well, in the local universe, we have detected or characterized this scaling relation between black hole mass and galaxies' dynamical properties, like velocity dispersion, or galaxy mass, or bulge mass. However, this scaling relation is only well characterized in the local universe. And we would certainly like to know what this scaling relation looks like in the high redshift universe in order to figure out the relative growth pace of galaxies versus supermassive black holes. In other words, like which one of them grows in the first place and the other one catches up later. So the second thing is that why we should care about how fast the black holes are growing. Well, this is because the black hole feedback, or AGN feedback, is very commonly invoked in lots of theoretical models, like hydro simulations or semi-analytical models. But the dominant or the main feedback mode from AGN or black holes is actually a strong function of the specific accretion rate of black holes, which is basically the black hole accretion rate divided by the black hole mass itself. So in order to figure out, or effectively, this is also the Eddington ratio. So the way it works is that generally lower Eddington ratio implies more kinetic feedback. In other words, the black holes is going to impart more kinetic energy than radiation to its nearby environment as a kind of feedback. So in order to understand the dominant AGN feedback modes in different kinds of galaxies, we not only have to know how big these black holes are in different galaxies, but also, at the same time, how fast they are growing. So basically, to answer this how big and at the same time how fast these black holes are growing question in different galaxies, we built this Trinity model to basically build mock universes where galaxies and supermassive black holes are put into dark matter halos and then self-consistently evolved along the statistical assembly histories of dark matter halos. So we built such mock universes for millions of times in the Markov chain Monte Carlo algorithm. and compare the mock universes with the real statistics of galaxies and supermassive black holes. So via this kind of comparison, we try to characterize the best way to map galaxies and black holes back onto the dark matter halos that achieve a best match between our predicted or mock universe and the real observations. So the incorporation of as many data sets from galaxies and black holes as possible is really important here because it helps us to break lots of degeneracies in the model parameter space. So for example, if we start from the star formation histories in different halo populations, which is already constrained by Peter's universe machine model, we can then use quasar luminosity distributions in different galaxy populations to specify how fast the black holes are supposed to be growing in these different kinds of halos or galaxy populations. In other words, we can constrain the black hole assembly histories in different galaxy populations across cosmic time. However, there's an obvious degeneracy between the AGN radiative efficiency, which you must use to convert quasar luminosity into the physical black hole accretion rate and the black hole accretion rate itself, because you can always get the same quasar luminosity by tweaking the AGN efficiency and the black hole accretion rate by the same factor but in the opposite directions. So basically, to break this degeneracy, we use the scaling relation between the black hole mass and galaxy bulge mass at redshift 0 to specify how much black hole mass at the end of such assembly histories should be in place for different galaxies. So by combining these mass constraints and luminosity constraints at the same time, we can simultaneously constrain the normalization and also the shape of such black hole assembly histories in different galaxy populations. So that's basically an example of how we break the degeneracies in our model parameter space using different kinds of data sets for AGN. So by using so many different data sets from both galaxy side and the AGN side to constrain our Trinity model, the first thing we can predict is certainly the mass connection between galaxies and black holes across cosmic time. And it seems that according to Trinity, this black hole mass versus galaxy mass relation doesn't really change a lot over the redshifts. But Trinity can actually do more than just giving you a best predicting or best fitting model, because effectively Trinity has created a mapping between our observational data constraints from galaxies and AGNs and our model predictions like the mass connection over the cosmic time. So with this mapping, if you propose another, any alternative redshift evolution of this black hole mass versus galaxy mass relation, Trinity would be able to predict all the observational statistics like quasar luminosity functions based on this proposed redshift evolution and tell you which part of the data constraint is inconsistent with our model predictions, which would tell you why is this alternative redshift evolution implausible, or which part of the data constraints is breaking. And if we use this constraint, or if we use this mapping between the input data and the mass connection in the other way around, we can actually understand how this mass scaling or the redshift evolution of this mass scaling would change in response to any potential change in our input observational data set. For example, if we switch the waveband through which we get the quasar data, like switching from X-ray to UV or even infrared, what kind of systematic effects we would get that would get reflected on the resultant connection between black hole mass and the galaxy mass. So beyond mass connection, as I promised, Trinity also predicts how fast the black holes are growing in different galaxy and halo populations, which I'm visualizing here as the average Eddington ratio of all the black holes, regardless of whether they're active or not, in different halo populations across the redshift. So in the high redshift universe, black holes are basically accreting at a uniformly high Eddington ratio, regardless of their halo masses or their black hole masses. But we do see a decline in the Eddington ratio towards lower and lower redshift universe, firstly among the massive objects, and then gradually towards smaller and smaller black holes, galaxies, or halos. So this is also consistent with what we found in observations, which is also called the AGN downsizing effect. Okay, so finally, if we look at the low redshift universe, and especially among the massive halos or galaxies, we can actually see that their Eddington ratios of black holes are really low, and this is also consistent with the scenario that the black holes in massive galaxies in the local universe or low redshift universe is predominantly exerting kinetic feedback, in other words, imparting more kinetic energy than radiation to their galaxies to prevent them from forming too many stars. Okay, so I think in the interest of time, I will just stop here, and I'll give a summary including other points that I don't have the time to cover, but please feel free to ask about them if you're interested. And thank you so much for your time. Yeah.
So, Haowen, the Webb telescope sees those galaxies above redshift 10, between
Yes.
10 and 17.
Yeah.
And they seem to be strange in the sense that they have more UV emission than you expect for the halo mass
Yeah.
associated.
Yeah.
And so obviously a possibility is that they have a black hole. Now you had this relation,
Yes.
and if you were to apply it to the, by abundance matching, let's say, to those galaxies that the Webb telescope sees,
Yeah.
could it explain the high UV luminosity that we see from them?
I think qualitatively, yes. So at the very beginning of those like high redshift galaxy paper that came out, I actually did a test because we now know, okay, so based on the information contained in Trinity, we can actually predict what are the luminosity distributions of quasars given their host galaxy mass, even say at redshift 10. So for example, there's a Lebesgue galaxy at redshift 10, I think claimed to be 10 to the 11th solar mass. So according to Trinity, actually you would see a significant portion of the James Webb NIRCam fluxes to come from the AGN instead of the galaxy itself. This is also, but in fact, we don't see a point source in the photometry. So that would be my argument against that galaxy being really at redshift 10 and at 10 to the 11th solar mass.
So it's an argument against Trinity.
Well, to some extent, yes. Depending on which one, well, whether you choose to believe what Trinity does or their observations.
Well, we tend to believe data, I guess.
That galaxy,
Okay,
well, that galaxy lost like 90% of its weight between the archive paper being submitted and the final version of the paper.
are we talking about the stellar mass or the halo mass?
The stellar mass. But I mean, there's some mapping. They assume nobody measured the halo mass.
Right, so what was the reason for the stellar mass being reduced so much?
Which is calibration of the campus.
So the other thing that the stellar mass could be wrong is the assumption about the star formation history, in addition to the IMF. I will leave the issue of IMF, but like star formation histories, I think for that 10 to 11 solar mass galaxy, they assume a constant star formation history. But if you instead assume a increasing star formation history, the figure will be much lower. So,
and of course, the way to settle this is using Chandra. If we expose for a long time, look at this galaxy. Okay, other comments, questions? Well, it looks like everything was very clear. Thank you so
All right.
much.
Thanks.
I don't think Chandler's detected anything.
So you want to? Oh, no. Yeah.
Well, the redshift 6 things. God. Millions of exposures. And well, specific large clusters.
All right, shall we get started? Hi everyone, I am Pipit. I'm a new postdoc here, and today I will tell you about my latest work on the dust contributions to the far ultraviolet to far infrared emissions from simulated galaxies using a semi-analytic model called dust-stage. And first, I have to tell you how dust is important, because as we see here in the beautiful Horsehead Nebula, how dust blocks our view of the galaxies behind it. And this will be like more better clearly viewed in the spectral energy distribution, or the ASAS of the galaxies, which is basically the distribution of the luminosity versus wavelength. So this is again far ultraviolet to far infrared, which contains information for example, like how the OB stars emit lights that peaks on the ultraviolet, while older stars, for example, like the red line there, emits in a much longer wavelength because of their lower energy. But what we observe is not like the blue or the red line, but like the black line, which is the absorbed, including the absorption primarily from dust. Now, dust absorbs these lights and gets heated and re-emit the radiation in a much longer wavelength, which is shown in the pink line in infrared or submillimeters. And this correction can really affect our derived properties from the observations. For example, this is the star formation rate density measured from UV in the blue dots and measured from the submillimeters, so infrared. So this does obscure galaxies in the red points, which is only complete until redshift 2. We see how in the redshift 0, it's kind of like smaller fraction, but as we move to higher redshift, this is really matters. So that's why we need to understand dust better. Unfortunately, when I started my PhD, I think most of the dust in simulations are neglected, and most are done in zoom in simulations, and we have no statistical data in from simulations. So what I do is I include dust processes in semi-analytic model, because semi-analytic model is faster and is a good way to test new prescriptions, in this case dust. The model is available there, and as Trinity, it runs on the post-process as a post-processing step for the dark matter halo merger trees from n-body simulations. The baryonic prescriptions is adopted from SAGE. So this is a Proton 2006 model, including infall, star formation, feedback, and everything. And then I include several dust processes like the grain growth, formation in stellar ejecta and supernovae, and the dust destructions in thermal and supernovae shocks. Now, the model produced scaling relations like the dust mass functions. Now, there are several models that do this. We can track that across the look-back time. But in this talk, I will tell you about the mock ASAS and luminosity functions from the model that is extracted using a pipeline called Mentari, which is also available in that GitHub. So what Mentari do is, first it extracts the star formation histories and metallicity histories from the millions of galaxies from dusty stage, which looks like that, for the spiral and elliptical samples. And then using that histories, then it assembled the spectrum from the stellar populations from the Brujuel and Charlotte 2003 models. So then we have the intrinsic stellar spectrum, right? But then we have the dust mass and like radially, so we can compute the dust surface density from the model. And the goal for this is to test all of the parameters that influence dust, and also test the translation between this dust surface density. Sorry, where's my dust surface density and the attenuations. So I tested two prescriptions. So first is from Eagle Hydro, and the second is like more empirical, constrained by the UV luminosity function. And as the benchmark is the constant attenuation that is usually used in a model. So just assuming 0.3 in attenuation in the optical, I think in the V band, which is the value from Charlotte and Fall 2000s. And then we tested like different infrared emission. One is from like more empirical work, and like the blue line here and the orange line here is like more theoretical. So then we have all of the different models here. So the black line here is like the black line here. The red line here is like the red line from the model with red line here. So let's zoom in to the results. If we look at the near infrared and optical, we see that how all of the models are like cannot be distinguished because they lie on top of each other. So it is shown more clearly in the luminosity function. So K band is basically all stellar, it's very insignificant effect for dust. But as we decreasing in wavelength, then we started to see like difference in the model, and how the black and red line here are like the better description for the data, because it changes the dust attenuation with the dust mass in the galaxies, right? Which is kind of like what we expected. This effect is more prominent in the UV because of like more significant effect of dust. Here in the for UV and NUV, it shows like, again, we can improve the fixed attenuation or like the constant attenuation with using like the red and black line. In the mid-infrared, our model is far behind, like far below the data. It's because like this is where the AGN component starts to pollute the acids. So we did like a simple toy model where this is like the mid-infrared 3.6 to 8 micron. And we see how in 8 micron, this is like the big difference, where the big difference is. And that is because we assume the AGN fraction in all of galaxies in this Fujicell model is 0. But if we increase the AGN fraction in this toy model with this like to 0.5, 0.8, and 1, it shows that how like the big difference are happening in the 8 micron. So yeah, it's like increasing effect of AGN contaminations with wavelength here. So this should be like improved in our model next, the AGN model. And then in infrared, our model is basically like better if we use the theoretical descriptions. So this is all in redshift 0. At high redshift, this is like where we have to play with the parameters, because the models in its current state cannot simultaneously match all of the data in all of the redshift. So for example, this is the K-band. Remember, K-band is like all stellars, no dust effect. And it is shown here that we do not produce enough massive galaxies at high redshift with our current model. So what we do is we increase the star formation by decreasing the feedback. So this is decreasing the radio mode efficiency to 1%. This is still like the range that is shown in the observations, and we can match the data better. So like the goal for the semi-analog model is not to match everything, but to know which parameter is sensitive to which properties. And like, so in far UV, for example, here is like the same color. So the radio mode efficiency 8% is the black line, and the green line is 1%. Now, both lines cannot simultaneously match everything. So like here, like the green line is over-predict, while here the black line is under-predict. So then in UV, remember, like dust is really important. So we should play something with the dust parameters. And the red line there is the model with radio mode efficiency 1%, so like lower feedback, and in like no dust destructions, so like more dust. So I guess like the takeaway, because like we still like need more observations and better modeling, the takeaway is we can like semi-analytic model is a good tool if we want to like change the parameters and see what is the effect in the overall properties of like the model galaxies and how it compares with data. And then we see that in our model, like using the changing attenuation with the dust mass properties in the model works better than just using like constant attenuation, which is what we expected. But then the model could be improved if we want to improve the SED. It should be improved like in the AGN fractions. And the feedback and dust processes still needs tweak to simultaneously match everything if that is our goal for next. So yeah, that's it.
Dian, you didn't mention how the models predict the evolution of the metallicity, because that should definitely calibrate the amount of dust. So if we go to very high redshifts, there isn't much metallicity, and then there will be less of an effect of the dust. I don't know if that is seen in the data or not.
Yeah, so the dust to gas and the dust to metal ratios from the model, this is like another work, but from my previous work, it is shown that it evolves like at high redshift. So the dust to gas and versus metal ratios, I think it's like plateau, like there is like this critical value of metallicity where above that, the dust is like very sharply increased because the dust production mode changes from stellar eject, from like forming in stellar ejecta and supernovae to like grain accretion, like it accretes more metals in its mantle, so it increases mass through that mode. So yeah.
So do we see that in the universe?
We see that in the model.
Oh, that's very interesting.
Yeah.
Because in the gas phase, of course, it will not happen at very low metallicity, but obviously, as you said, the stars will still produce it in their envelopes.
Yeah.
Very nice. Okay. John?
Just wondering about the spatial distribution of dust in galaxies, because it's clumpy in the Milky Way and nearby galaxies. So do you have line of sights that you see through and line of sights that are very obscure? Does that play a role in this story?
So in this study, unfortunately, we cannot spatially resolve the galaxies. So because semi-analytic model, we just like have one properties for one galaxy. So it sees the galaxy like as one big bucket. But using a hydro, then like we have to like really step up our simulation scheme. So just with this semi-analytic model, use a more complicated models to see like the spatial resolution, but that would be like real interesting.
Thank you.
Any other comments, questions? Not, let's thank Dian again.
The screen is turned off. All right. Hi, everyone. My name is Dominic Rowan. I'm a third-year graduate student at Ohio State. I work with Chris Stanek, Chris Kochanek, and the rest of the ASAS-SN team. And today I'll talk a bit about some of the work we've been doing the past 2 years or so to study eclipsing binaries with ASAS-SN. The big idea here is we're interested in measuring the fundamental parameters of stars. We want to develop and improve our models of stellar structure and evolution. I want to understand the physics of effects like convective overshoot and mixing and mass loss. And the best way to do this is going to be to measure masses and radii, make comparisons to these models. We need to do this across the color magnitude diagram, so stars have different mass, have different metallicity, and have different evolutionary state. And the best way to measure precise stellar parameters is to use detached eclipsing binaries. The idea is we can take two stars that have evolved effectively in isolation, combine their light curve with their radial velocity curve, and this gives us the individual masses and radii of those two stars. Now, pretty much every photometric survey has compiled large catalogs of eclipsing binaries, so space-based missions like Kepler and WISE, and ground-based observatories like ULGO and ASAS have found tens of thousands of these, usually as part of some variable star classification scheme. My favorite photometric survey, and I hope yours is too, is ASAS-SN, the all-sky automated survey for supernovae. I put some basic stats for ASAS-SN up on the screen, but the big idea is with ASAS-SN, we're observing the entire sky in optical light with daily cadence. And so ASAS-SN is a great tool to study the variable universe. And indeed, my good friend Trinity and former OSU graduate student compiled the ASAS-SN V-band variable stars catalog a few years ago. This contains over 400,000 variables. Their machine learning classification and their sky distribution is shown here. This catalog contains over 40,000 detached eclipsing binaries. This is a great sample to work with if we're interested in investigating the distribution of binary parameters. And so while there's been all these improvements in measuring large quantities of eclipsing binaries, there's also advancements on the computational side of things. So we have tools like PHOEBE, where we can discretize the surface of binary stars of different morphologies, use them to compute the expected light curves or radial velocity curves. We can also solve the inverse problem, so given some observational data set, we can predict the properties of the binary system. And PHOEBE and similar tools have been applied to dozens of systems or a few hundred systems. Our goal here is going to be to say, let's apply PHOEBE on a large scale to tens of thousands of ASAS-SN eclipsing binaries. And so the idea is to create this kind of flexible but simple pipeline so we can quickly and accurately measure parameters of binary systems. So we combine some different estimation tools with just an optimization process. We also do visual inspection of all of our light curves, and this wasn't just to drive myself insane, but also because it's an opportunity to improve the quality of the entire sample. And we also found some unique binaries, like with pulsating components or spotted stars. And so this figure is showing some of the examples of our light curve fits. In practice, ASAS-SN has a V-band and a G-band light curve for every point on the sky, and this figure is just showing one of each. And we can see that our pipeline is fairly effective at estimating parameters across the parameter space. So eccentric binaries like this one on the top left. We have a number of binaries kind of approaching the semi-detached limit in our sample, like this one in the middle. So we have these wider eclipses, this increasing amplitude of ellipsoidal effects. And we also have systems where there's a large difference in effective temperature ratio, right? So the eclipse depths here have a pretty dramatic depth or difference. And so in total, we report the parameters of more than 35,000 detached eclipsing binaries. And I want to emphasize here, we're not just saying, here's the eclipse depth in units of flux or the separation between the eclipses in phase. We're solving for physically meaningful parameters of these binary systems. So things like the sum of the fractional radii, the ratio of the effective temperatures, and the orbital eccentricities. And this allows us to start to explore some of the distributions of binary parameters. So for instance, this shows the entire sample and the periods and the eccentricities. So our points are those black dots. We also compared to a sample of spectroscopic binaries. This is the SB9 catalog, the open red circles there. And the general idea is that you see, right, as you move towards shorter periods, we have fewer high eccentricity systems, and this is just due to tidal circularization. So we also see that our sample is consistent with that blue line, that envelope that's expected from those spectroscopic binaries, although we have fewer long period eccentric systems in this eclipsing sample comparatively. And this is just going to be a selection effect of observing eclipsing binaries. We can also start to consider how these distributions of binary parameters change with evolutionary state. So we cross-match our catalog with Gaia early data release 3 at the time. So for instance, one thing we found was that the ratio of effective temperatures, that distribution was strongly peaked at 1, and then there was this kind of broad Gaussian component at like 0.6. And so in this figure, the binaries are colored by that ratio of effective temperatures, so the bluer points have large differences in eclipse depths. And right, we see that these systems are concentrated on the upper main sequence. And this is fairly intuitive. If you have two stars and they need to have a large difference in effective temperature, the hotter star has to be fairly hot. But another reason that we're interested in combining our catalog with Gaia is this allows us to tag each system as having photometric primaries on the main sequence, the subgiant branch, or the giant branch. And so those are all those solid and colored line divisions. This is another way you can interact with our catalog. And a big motivation for this work was making all of our results easily accessible and public. So we have this online database. The link is up there, or if you Google ASAS-SN, it shows up. And the idea is you can, well, either download the full sample on all their light curves or search through individual systems. So if you're interested in observing, say, eccentric binaries on the main sequence, that's an easy query, or the longest period giant branch systems. You can also inspect the individual light curves. So you can see their position on the CMD, download the light curves and their PHOEBE fits. And so we hope that this is generally a useful tool for the community. But I opened this talk by saying we want to measure masses and radii of stars to make comparisons to stellar models. So far I've just talked about the eclipsing binary light curves, and that missing piece that we need is the spectroscopic information from radial velocities. So one way to approach this is to do dedicated follow-up of individual systems. This is something we are pursuing, but it's also interesting to see if we can combine large spectroscopic catalogs with ASAS-SN. And so Gaia DR3, released last June, includes over 5,000 double-line spectroscopic binary orbits, and this is exactly the information we need to get masses and radii. And so this figure shows the apparent magnitude distribution of our sample as the blue histogram. The Gaia SP2s are shown in black. And the idea here is we're kind of operating in the tail of these two magnitude distributions, really the faintest Gaia SP2s, the brightest ASAS-SN eclipsing binaries. But this gives us a sample of about 130 binaries to work with to start. Kind of the caveat with Gaia DR3 is that we don't have the epoch radial velocities. We just have the results of their double-line spectroscopic orbit fit. This means we have the velocity semi-amplitudes, which is what you actually need to get the masses in the radii, but we can't say for a given system, should we trust them, right? We can't see the data underlying the model. So one way we can try to flag systems where we believe the Gaia orbit results is to compare the periods and the eccentricities that they report to what we get from the ASAS-SN light curve fits. And so this figure on the top is showing the comparison of the periods. The bottom is the comparisons of the eccentricities. And we found that only about 50% of those systems where we have ASAS-SN and Gaia have agreement between the periods and the eccentricities. And this was fairly surprising. It's difficult to say what went wrong with a given Gaia orbital fit, right, if we can't see the data that produced it. But I will say that similar results have been seen for the single-line spectroscopic binaries, which is a much larger sample of about 180,000 stars. So for those systems where we do think we can trust the velocity semi-amplitudes that Gaia gives, we can use them to derive masses in the radii by just combining them with our existing PHOEBE model. And so this figure shows the masses in the radii of 122 stars as the black points. For comparison, the red squares there are the kind of premier sample of detached eclipsing binaries, where the fractional uncertainties are within those little red squares. So comparatively, we're not quite on that level. We're getting median mass errors of about 8%, median radius errors of about 6.3%. But I think it's important to remember that what we've done here is we've taken data from two large publicly available surveys. And this allows us to get an expanded sample of stars. This also is a good opportunity to push into regions of this parameter space that are undersampled, like the giant branch. So we had 12 giant stars with this sample, and this is definitely an area where there's few systems with dynamical masses and radii. And so with that, I think I'll leave my summary slide up. I'll stop here. I'm happy to take any questions.
Is this sample good enough to calibrate distances to a high enough precision to say something about the Cepheid calibration or anything else?
Yeah, that's a good question. So yes, Cepheids, the eclipsing binaries are a good distance indicator. I think that's something we're pursuing with giants in particular. So there aren't the giants that we have in this sample are a good starting point, but one thing we're doing now is actually getting RVs of giants. So that's something we haven't done, but we could.
So it might be relevant to cosmology as well.
Yeah, exactly. Yeah, most of the giants that do have dynamical masses and radii are in the Magellanic Clouds for that reason.
Yes, there are two questions. First, Michelle, and then.
I noticed in the period eccentricity diagram, it looked like the ASAS-SN data points had a higher envelope than the other. Is there a reason for that?
Yeah, that's a good question. I can jump back to that slide. I think part of the reason is we're not doing a full optimization here. So many of those systems that are just above the blue line don't have excellent eccentricity determinations. I think it's also true that part of the determination that you get for eccentricity out of the light curve doesn't just come from the difference in the phase of the two eclipses, but also in the relative widths, right? And so this is something where if we use test light curves, we might be able to get a more accurate eccentricity determination. So that's something we could definitely do for just those systems that lie above the blue line.
Please go ahead.
Yeah, so I have a very naive question. So you seem to be able to characterize the, say, the temperature ratios of each of the stars in the binary system. So is this kind of information informative for, say, theories of binary evolution?
We hope so. Yeah, so I think the temperature ratio distribution is something that's already been previously looked at. It's kind of one difference between our distribution and something that's seen before is that presence of this broader component at low temperature ratios. I don't have a huge insight on to how that relates to binary formation. One thing I will say though is that a lot of these systems that are bluer on this figure are starting to approach the semi-detached limit, so that they have increasing evidence of maybe mass transfer histories, and so maybe that could be useful there.
Oh, thanks.
Go ahead, John.
So this is actually very interesting to me. When you reported eccentricity, you must be using more than phase difference between the primary and the secondary.
Yeah, exactly.
What information does go into that?
The eccentricity is determined not only from the difference in the phase of the two eclipses, but also in the relative widths of the two eclipses, because it'll depend on the argument of period-Eccentricity, like the orientation of the binary. So that's included in the
How
theme.
good are those typically?
Sorry?
I mean, what errors would you typically report on eccentricity?
Well, so our catalog, we don't report errors because we're just doing like a Nelder-Mead optimization. We're not doing MCMC. So.
Thank you.
Go ahead.
Yes, go ahead.
Will ASAS-SN be superseded by LSST in the south, or do you have a different cadence for?
Yeah. Now, we have a different cadence. So with ASAS-SN, we have daily cadence, a little bit more certain areas of the sky. But the main difference between LSST and ASAS-SN is the magnitude range. So we're looking at, the ASAS-SN was designed to look at transients, right, based on the name, not eclipsing binaries. And so, we're looking at targets that it's easy to get spectroscopic follow-up from a variety of ground-based instruments. LSST is a bit fainter. But I don't have these specific numbers, so if anyone else knows the magnitude range of LSST, feel free.
Anyway, it's beautiful work, and let's thank Don again.
All right. So I'm Michelle from Northwestern University, and I'm excited to talk about something completely different to what I talked about earlier, the irradiation instability of protoplanetary disks. This is something I've been working on with Yoram Lithwick at Northwestern. ALMA has really changed the game in terms of what we know and understand about protoplanetary disks. No longer just kind of fuzzy surfaces. Now we can see evidence of lots of different types of substructure, lots of intriguing gaps and rings. And one exciting explanation is that maybe for every gap, there's a planet. This would be hugely exciting. It's a little difficult to disprove because you can always just kind of change the parameters of the planet, maybe make it a little more massive, change its location. But another option for explaining these kinds of features is a thermal instability, or an instability in the disk. That might not sound as exciting, but I hope to convince you that it can be. So it can solve or help to solve two main outstanding problems in the science of protoplanetary disks. One being, how do you create an environment where you have particle traps where dust can actually coagulate to start the planet formation process? So if you have some kind of gaps in these disks, then that might be a signpost of particle traps where you have a good environment for planet formation. And then another would be if these waves are, if you have a thermal instability and you have kind of waves in the disk that are hydrodynamically unstable, then they could produce turbulence. It's still a little unclear why disks accrete and why they go away on the timescales that they do, although we know that they dissipate. We know kind of vaguely the timescale which they dissipate. So this having a thermal instability in the disk could be a way to produce turbulence. Okay. There's some pretty successful models of protoplanetary disks that explain some of the broad features. So these disks are passively heated, so in a sense they are kind of simple to model. Most of the energy is coming from the stellar irradiation. So for a passively heated disk, you can think of it in terms of you have a region up higher in the disk where micron-sized particles are interacting or absorbing the starlight, and that's creating a heated layer. And then that heated layer is then heating the rest of the disk below. And that gives you a relationship for the midplane temperature and for the flaring index that goes as a nice simple power law. It's kind of described here below. But when you actually try to model these disks, that can become difficult. So if you try to iterate between thermal equilibrium and hydrostatic equilibrium, then you find that in a lot of these situations, you actually tend to develop an instability. So this was first seen or pointed out by Watanabe and Lin to raise the possibility that maybe instead of just kind of a numerical instability that we're seeing, this is a signpost of a real thermal instability in the disk, that there's a physical reason why a passively heated disk would be unstable. And a recent paper from Yangxin Wu and Yoram explains this instability and some of the mechanism behind it. So a way to think about this is what happens if I place a bump, so a bump in temperature and a bump in corresponding bump in the scale height of the disk. Then what happens? How does it evolve? Does it go away or does it grow? And throughout this discussion, remember, cooling goes like T to the 4th power. So cooling can be pretty efficient. If you have a little temperature perturbation, maybe like 4 delta T over T. So if you have a perturbation to the disk or a perturbation to the photosphere, there's going to be 2 pieces here. One from the change in scale height and one from the change in this ratio chi, which is the ratio of the photosphere to the scale height. And we can see what happens with each of those pieces. So from the piece where the scale height increases, if the scale height increases, it goes as temperature to the 1/2. So if that's the only change that's happening when we place this little bump in the scale height, then you would imagine that the effect of cooling is going to be able to kind of get rid of any temperature perturbation that you have. However, and I should point out before I move on that a lot of work has just looked at this effect and held chi constant. So said that the photosphere, the ratio of the photosphere to the scale height has to be fixed. But if you relax that assumption, if you say, well, instead of just assuming that, I want to actually calculate once this disk is in thermal equilibrium, where is the new photosphere? Or once it's in hydrostatic equilibrium, where's the new photosphere? Then you see another interesting effect. So you can kind of get a sense from this here. When you have this bump in the disk flares more steeply on the inner edge. So not only does the starlight see more surface area, it also penetrates deeper onto this front edge than to the shadow region behind. And it's that effect that allows an instability to occur. So under the right conditions, a perturbation in the disk can grow in amplitude, and it will travel inward as this area is heated more and puffs up and kind of moves inward over time. So we'd like to model this instability with a time evolving disk. So here's a few of the assumptions that have gone into a relatively simple model. There's a few main equations here that we can group as this is equations for radiation transport, one for the light that's coming from the star to see how much light is being absorbed, and then another to adjust for hydrostatic equilibrium at each time step. There's a few challenges with modeling radiation transport in the system, and the big one is how do you handle radiation transport that goes through both the optically thin and optically thick region? So you have this surface that's high above the IR photosphere of the disk where the sunlight is intercepted. That's the most important for intercepting starlight through these micron-sized dust grains. But then really we're interested in modeling what's happening below the IR photosphere, and there can be a significant gap between those two regions. There's a few solutions that we looked at and that have been done in the literature in different contexts, ways of bridging optically thin and optically thick regimes. And these are all kind of approximate, but they will give you the right answer in the optically thin regime and the right answer in the optically thick regime and give you a way to go between the two. So we have taken a different approach. We're not using these. We have decided to solve this problem by trying to avoid it. So the way that we do that is trying to analytically determine, without needing to include this region in the code, what the incident flux should be at the IR photosphere of the disk. So here you have a disk. This is density. Here's the optical surface, and here below the IR photosphere. So we want to know what the flux should be at the black surface. And the way that we do that calculation is to do an integral over all of the rays that are originating from the optical surface to see what the flux should be here, assuming that in this region between the optical surface and the IR photosphere, there shouldn't be a lot of absorption. So this is the integral below here. So this is the equation that we use to calculate what the flux should be at this boundary. So this basically works as a boundary condition in our code. So we're able to put that in and then only need to model this region of the disk where everything is optically thick in the IR. So here is one of the results that we get for a sample disk. This is a little bit of a toy disk to make things run faster, but you can see here that there's some variation in the temperature, these kind of waves in color. And then if you look at the temperature evolution over time, you can see here is what's happening to the temperature at the photosphere. So you have these variations that are traveling inward. And then to a lesser degree, these still persist in the midplane, where maybe this doesn't show up quite as well on the screen, but you can kind of see the ghosts of these waves at the surface that have penetrated to the midplane. And we're exploring what conditions you need to ensure that that penetration to the midplane actually happens, because that's the case where you could have temperature variations throughout the midplane, density variations, and maybe create a pressure gradient in the disk that could produce gaps and rings. So some next steps that we're looking at is incorporating dust settling. So far, we're assuming that dust and gas are tracking with each other, but really there should be some dust settling in the disk. We think that this might lower the optical surface and promote instability. And then we also are working on incorporating hydrodynamics. This is a work in progress, and that would allow us to confirm that these vertical thermal waves can actually reach the midplane. Thank you.
So Michelle, could this instability lead to enhanced planet formation, or do you think it does coagulate?
I think so. So the idea is that you need a way to form the first planet. So once you already have gaps and rings, then you have a scenario where you probably have dust traps and can have continued planet formation. But yes, the idea is that this could be a way to create an environment where you could form a planet without other planets being in the disk.
Comments? Questions? If not, let's thank Michelle again.